In this problem, we have a fuel oil with some properties that are given is being pumped through a 2.5-inch Schedule 40 pipe for 500 meters at 3 kilograms per second. And then the discharge point is 5 meters above the inlet, and the source and destination pressures are both at 101 kilopascals. If the pump is 80% efficient, what is the power required? And so we have our little schematic here. There's a 5-meter change in elevation. We are told that it is just the 2.5-inch Schedule 40 pipe, so assume it's the same diameter at both ends. 500 meters, we aren't told how much is on each side. We'll see in this case it doesn't matter because we're just going to calculate the total losses, head losses due to that single length. We don't really care whether it's on the inlet or the outlet side. So we can assume that position 1 is a tank that's upstream, position 2 is a tank that is downstream. We have no information given about fittings in the line, so we're not going to include that. We're just told that the length is 500 meters. And so what we can do is we can apply Bernoulli's equation. And so here's our Bernoulli equation from position 1, where we'll say that it is here to position 2. And we can then start to look at terms to cancel out or simplify to a 0. If tanks are involved, of course, if we had a tank here at the inlet and a tank at the outlet, then the velocities at those positions would be 0. But even if we didn't, even if we were just limiting ourselves to what's going on in the pipe, the inlet and the outlet pipe IDs are the same, and so the velocities, because we have incompressible flow and steady state, I didn't say that explicitly, but in all these problems we should be assuming that it's steady state and incompressible flow for liquids. Those velocity terms are going to cancel out. So the u1 squared over 2g and the u2 squared over 2g, those are going to cancel out. And then we're going to set the datum at the pump level, and so our z1, which we're assuming that the inlet is going to be the same height as the pump, is going to be 0, and our z2 is going to be 5 meters. So we do that, we make those simplifications. Pressures, the velocities cancel out. All we're left with is the head added, which is going to be the head by the pump, minus the head loss is going to equal to the elevation change. And I forgot to mention, but there's no head extractor, there's no turbine or expander, so we can neglect that. So what we need to do then is we need to calculate the head loss, right? The head loss, and that's going to be just due to friction. We're not told anything, and that's friction in the pipeline between the fluid or oil and the pipe walls. So to do that, we need the linear velocity and the Reynolds number of our fluid flowing through the pipe. And so what do we know? We know the mass flow rate, right? We know the mass flow rate. We also know the diameter. So we can calculate the linear velocity. We calculate the cross-sectional area of the pipe. And also notice, again, I didn't mention this, but notice that we're dealing with Schedule 40 pipe, and so we need to look up that the nominal inner diameter is not the actual inner diameter. So make sure that you don't make that mistake. Make sure you look those things up. We calculate the cross-sectional area. We know from the continuity equation that the mass flow rate is constant, so we can calculate the linear velocity, which is valid for the entire system, is 1.08 meters per second. We then calculate the Reynolds number. The Reynolds number is rho v/d over mu, or rho u if you're using u for velocity. And so we get a value of 870. And this is a lot different from some of the water calculations that we dealt with. This is oil. And so when we're dealing with oil, we will sometimes run into laminar flow. Remember, laminar flow is somewhere around 22,000 to 2,300 this is definitely laminar flow. And the reason is because with oil, our density is lower and our viscosity is usually higher. And so we will more often run into conditions where we might have laminar flow. So what this does is this makes calculating the friction factor and the head losses due to friction a lot easier. And so it's a lot simpler equation for the laminar flow. It's just the fanning friction factor is equal to 16 over the Reynolds number, or a value of 0.018. We then calculate that, or sorry, plug that into our equation for the head loss. And notice I like to use head loss with G in the denominator so that I have the same units as what I have in my form of the Bernoulli's equation that I use. Your book does not have G in there and will have different units. So anyway, over the 500 meters, our head loss due to friction is 34.82 meters. If you want to compare the kind of do an equivalent length type of comparison of what the head losses are due to the total length of the pipe. So from that, we now can plug that into our head loss and calculate the head added for the pump. And so we get 39.82 meters of head need to be provided by the pump. And again, we've done this several times now to convert head added, or head in general, to power. We take the head, we multiply it by the weight of the fluid, which is rho times G, and then we multiply it by the volumetric flow rate, which is the velocity, linear velocity times the cross-sectional area. And so we get the head required for the pump to be 1.71, and I could put this in kilowatts. Let's put this in kilowatts. So 1.7 kilowatts, or remember, we have a pump that, excuse me, this is the power that's required to move the fluid, but our pump, I should say, is only 80% efficient. And so our pump is going to have more power input into it than just what is required to move the fluid. So we divide that by our efficiency of our pump, and we get a value of about 1.4 kilowatts. If we wanted to put this in horsepower, we can get a value of about 1.96, or about 2 horsepower to move this oil.